Welcome to qnawire.
So we have an electron entering a solenoid, and so we know whenever that happens, or whenever an electron enters a magnetic field, it's going to make a helical path. And so we want to find then the radius of that helical path as well as the pitch, or the distance between spirals. So we'll start by finding the radius for part A. And so first we know that when an electron or any charged particle is in a magnetic field, the force on that is just q, the charge of the particle, times its velocity, times the magnetic field, and then times sine of theta, where theta is the angle between the velocity and the field. And so we know that this is going to make it move in circles. And so that means this must be equal to a centripetal force. And so this has to just be equal to m v squared over r. And v here, though, is just the velocity that's tangent to the circle. So we'll call this v perpendicular. So the whole electron is taking some helical path like this. So there is a perpendicular velocity that's responsible for it going in these circles. And then there's also a parallel velocity that's responsible for it moving through here. So this is just giving us the perpendicular velocity, the part that makes the circular motion. But so from this we can find what the radius of the circle is. And so it looks like that'll come to be m, so the mass of the electron, times this v perpendicular. So really v times sine of theta is just v perpendicular. So we get 1v perpendicular when we cancel those. So we just have a v sine of theta, and that's over qb. And that should come out to be 2.734 times 10 to the minus fourth meters, or just over a quarter of a millimeter, 0.27 millimeters. So now for part B, we want to find the distance between each of these loops, so what this distance d is. And to do that then, we can just say, well, we know that in general velocity is just distance over time. And so the time in this case is just going to be the time of one of these loops. So during the process where the electron is making one of these loops, it's also moving forward. And so in every loop, it moves forward this distance d. So it's just the period of its cycle in terms of like going in a circle like that. So distance is just its velocity, and this will be its parallel velocity. So how fast it's moving in this direction, and then divided by the period. So that'll be the cosine of theta. And, oh, whoops, no, this should be times t. There we go. So yeah, multiply by t on both sides here. So we have our parallel velocity and now our period. And so our period should just be the circumference of the circle, 2 pi r, divided by its perpendicular velocity, so v sine of theta. So that's just a normal circular motion equation. It's in one cycle, it's traveling the circumference, 2 pi r, and it's moving in that plane with velocity v sine of theta. So we can reduce this to 2 pi r over tangent of theta. And when we plug in all of our values for there, we'll get about 1.4 centimeters. So it's making these very tight loops of just over a quarter millimeter, and then it's moving 1.4 centimeters in each one of those. So this picture probably looks a little bit more, maybe something like this. Be a little bit more accurate. But either way, there we go.